Hello, welcome to the second lecture on network theory. So, in the previous lecture, we talked about the different network elements or circuit elements that we are dealing with in this lecture. So, we considered or we gave some basic definitions regarding the different types of sources and different types of sinks. So, we considered voltage source, current source, AC source, DC source, and we considered resistors, inductors and capacitors, right. So, now let us move on and see some more definitions. Okay. So, the first thing that we will be dealing with is the concept of a node, right. So, what is a node? A node is the point of interconnection between any two or more elements, right. It is the point of interconnection between any two or more elements. So, let us consider a figure. Let us consider a network or a circuit. Right. So, if you see here, we have one node here, another one here, another one here, right, and these three, right. These three are not separate nodes, they are one single node. So, if you look here, we have a node with an into which three elements are connected. Here also three elements are connected. Here only two elements are connected, but here 1, 2, 3, 4 elements are connected to this node, right. So, node the thing is that there should be a minimum of 2 elements connected to that particular point. So, that is a node. So, here the lines we do not consider them as any component, right. So, basically there is no difference if you draw something like this, right. This is the same thing, there is no difference. I am just stretched out and rearranged some elements. So, basically these lines, right, these lines they do not have any value, or we do not consider them to be a separate element. They are, right, we consider them to be ideal short circuits, that is it, right. So, we are not considering them to be elements, only the we are considering only identifiable sources and sinks. Okay. Now, let us move on. The next idea or next definition is regarding a mesh and a loop, right. So, what is a loop, right? It is any possible closed path, right. It is any possible closed path of a circuit or network. It is any possible closed path of a circuit or a network. So, what is a mesh? Mesh is also a closed path, right. It is also a closed path, but there is a condition, right. It is a closed path which doesn't have any further closed paths. right? We'll consider an example. Okay. Okay, something like this. Here, so this here, this is a mesh again. This is a mesh, but this is a loop, right? Here within this mesh there are no other closed path, but within this one there are two other closed paths. We can find two other closed path, right? So that is a mesh and a loop. Like let's consider one more example, right? For something a little bit more complicated. Right. So here the meshes are these. This is a mesh, this is a mesh, this is a mesh, and this is a mesh. So which are the loops that we can find? So obviously this is one loop, this is another loop, this one here, this is another loop, right? So we can find many loops, but the number of meshes in a circuit or a network will be fixed, right? Will be fixed. But within the same network or the circuit, depending on how we are taking the path, we can find different number of loops, right? That is the difference between a mesh and a loop. So there is an equation relating this mesh or loop and node. So it is number of meshes will be equal to number of branches minus number of nodes plus 1, right? So what is a branch? So M is a number of meshes, N number of nodes, and B number of branches. So what is a branch? This is a branch, this is a branch, this is a branch, this is a branch, right? That is, every element is a branch. This is not a branch, right? This is a single point. This is a branch. So basically branch is every element, right? Number of branches equal to number of elements, let's say, whether it is a source or a sink. So this can be, this equation might come in handy like if it is asked. So just keep this in your mind, right? Okay, now let's move on to the next topic. I am sure all of you know about this. It is called as the Ohm's law, right? Ohm's law. So basically what is Ohm's law? Ohm's law is nothing but the relation between V and I, right? V and I. But remember one thing, when we are saying that Ohm's law is the relation between V and I, it is what? Specifically for our network theory, right? We are defining Ohm's law as the relationship between voltage and current specifically for this network theory, because we are deriving Ohm's law as the relationship between voltage and current for our purpose. So, we will see some different forms of Ohm's law. So, the first one is J equal to sigma E, right. J equal to sigma E. Okay, J equal to sigma E. Let me rewrite this as J equal to sigma E. So, here J is the current density, sigma is the conductivity, and E is the electric field. You may have learned about this, may not have. But anyway, you will learn regarding this in your higher semesters. So, from this we derive what we use as Ohm's law, V equal to Ohm's law, V equal to IR, right. This is for a resistor. So, from one form, so let us say first form J equal to sigma E, we derive, we can actually give what J equal to current by area, right. Sigma equal to 1 by conductivity, 1 by resistivity, and E equal to V by L, voltage by length. So, if we do this and we rearrange this, we can actually come to this form V equal to IR. But anyway, this is the form that we want, V equal to IR. This is the first form, and we use this for our resistor, right. The second form is psi equal to L I. Psi is the flux linkage, L is the inductance, and I is the current. From this we get V equal to L di by dt, and we use this for our inductor. Consider this as the second form of Ohm's law. And the third one is Q equal to CV, where Q is the charge, C is the capacitance, and V is the voltage. From this we derive I equal to C dV by dt, right, and that is what we use for our resistor, inductor, and capacitor. So, what we are doing is basically we want Ohm's law in the form as a relationship between current and voltage for our purpose of analyzing the circuit or network. For that we start from the basic equations pertaining to each element, right. We start with the basic equation, that is the relation between current density and electric field for a resistor, between the flux and current for an inductor, between the charge and voltage for a capacitor. So, we start from the basic forms in which the energy is spent for each component, and from that we come to the relevant part, that is the relationship between voltage and current for each element, right. That is Ohm's law, 3 different forms of Ohm's law. And these first parts, right, this one, let's use these 3. So, these 3 are called the electromagnetic form, EM, electromagnetic form of Ohm's law, and these 3 they are called the circuital form of Ohm's law. All these are Ohm's law, but this is the electromagnetic form. You will learn about this in your applied electromagnetic theory course, and this is the circuital form that we will be using for our course, right. Let's move on. Anyway, since we are dealing with basic definitions, let's do the basic definition for voltage, right. voltage is V equal to dW by dQ. That is, voltage is the work done to move a unit charge, right? It is a work done to move a unit charge. It is a work per charge, dW by dQ voltage. So basically, when it comes to our domain, just think of voltage as the as a driving force, as a potential, as some force that pushes the charges to move, right? So consider this: voltage is something as a it is an electromotive force, EMF, right? It is that force which pushes or drives the electrons or charges, let's say, not electrons, charges. So that is voltage for us. This is not much relevant. This basic understanding, or let's say qualitative understanding of voltage is required for you. Then the other thing is current, right? Current. And how is current defined? I is equal to dQ by dt, right? So under the influence of voltage, right, under the influence of voltage, that is, we are doing some work for a charge, right? We are doing some work on a charge, and if we are doing some work on a charge, or we are giving some force on a charge, what happens? The charge moves, and that movement, that results in what is called as a current, right? That is, we are applying some sort of effect, some sort of influence on charges, and we are making them move. And that movement, when it happens, it will have some rate of change, right? That is, it will have some velocity, it will have some speed. So current is basically the rate of change of charge. That is current. Rate of change of charge with respect to what? With respect to time, right? With respect to time. So you can change this rate of change to, you can use rate of flow also, same thing, depends on the situation, right? Rate of flow or rate of change of charge with respect to time. That is, consider this: we have a potential, or we have a voltage, right? We have a voltage, and we have some resistance, let's say, and if we are producing a current, it means this voltage is applying that much force, or that much electromotive force, EMF, to the electrons or charges, so that it overcomes the resistance offered by this device and it starts moving, right? That is, voltage gives the force to the charges so that it overcomes the resistance and it starts moving, right? On that part, what is resistance? What is resistance? Resistance is R equal to, right? Resistance is R equal to rho L by A, right? What is it? What is basically resistance or a resistor? It is a property of a material that opposes current, let's say the simplistic definition, right? It is a property of a material that opposes current. That is basically what is happening. We have a force, right? We have a force, EMF or voltage, right? We have a charge, or we have multiple charges, and the EMF or the voltage is trying to push the charge, but there is some resistance, right? Some resistance. So if there is enough EMF or enough voltage, what happens? This resistance, it overcomes this charge overcomes the resistance, and it starts moving, right? So if there is enough voltage, or if there is enough EMF, more charges will cross the resistance. That is the physical aspect. So the takeaway from this particular discussion should be that resistance is a property of a material, right? Resistance is a property. Voltage is the cause. Voltage is the cause. Let me just voltage is the cause. Resistance is a property, and current is the effect, right? This is a basic understanding that you should have, right? Even though we write V equal to IR, actually it is I equal to V by R. Like that is a basic thing. Like if you look at the this part, it is actually written as current density equal to something, right? Here we are just using it in this manner. Actually, when you are writing cos equal to something into effect, it should be I equal to V by R, but for convenience we are writing like this. So basic, but the thing is that voltage is the cause, current is the effect, and resistance is a property of the material, right? It's not like for a material, depending on the voltage and current, the resistance changes. No, it's not like that. Depending on the property of the material and the voltage applied, the current will change, right? So I equal to 1 by R into V, right? This is the cause, this is the effect, this is the property. I hope you understood. Okay, here what we said for resistance, it is the same for inductance and capacitance, in the sense that inductance and capacitance, they are also some sort of property, right? Inductance and capacitance are also some sort of property which affects the which along with the voltage affects the current, right? This resistance, you can consider, you can use impedance, right? I don't know if you have gone through that, otherwise we will go through it later, but anyway, consider that it is not just resistance, also inductance and capacitance are also property of a material, owing to which the effect, that is the current, will change, right? So then there one question you might have, or you should have at this point is, then what about a current source? A current source is something that gives a current, right? It gives a constant current, like a voltage source gives a constant voltage. Then if voltage is the cause, then how can you have a current source, right? That is a question you should have, right? At least that is something I had. So how can you have a current source if voltage or EMF is the cause and current is just an effect. So the answer of this you should give me, right? I won't give you, you should give me. If voltage or EMF is the cause, then how can you have a current source, a source which delivers the effect? It's in right, is in this statement an oxymoron? So find an answer and give it to me, right? Okay, moving on. The next term I want to introduce, not introduce, that you know already, is something called as power. What is power? Power is basically P equal to, you know this, dE by dt. E is the energy, that is dW by dt, right? That is, power is energy spent per unit time, right? Energy spent per unit time, or in other words, what does this unit time means? It is the rate of change of energy, right? And since we are dealing with circuits, what kind of energy? Electrical energy. So basically, power is the rate of change of electrical energy, or P equal to E by T, right? E equal to E by T. So what is the unit of power? It is watts, right? Not watt, watts, watt. Unit of power is watt. And if power is energy per time, then energy is equal to, what is energy? It is power into time. And the unit of electrical energy is kilowatt hour, right? This is the unit that you have, that you get billed by the electricity board, kilowatt hour, right? Or joules, joule, not joules, joule, right? Kilowatt hour or joule. So let's use small t here. So that is power. So when it comes to our network elements, what is the significance? Sources give power, sinks absorb power or energy, right? That's it. Okay, on that note, what is the unit of voltage? Volt, right? Volt. What is the unit of current? Ampere. And then what is the unit of resistance? Resistor or resistance? Resistance, right? Resistor is a device, resistance is a property. It is ohm. Ohm. And then what else is there? Inductance. Inductance is Henry. Capacitance. It is Farad. In practice, in practical daily life, we may use volt or kilovolt. if you remember in this electrical substations, it will be kilo 125 kV line, things like that. Current, amperage current is actually pretty high. If you look at your house residential electrical amperage current, it will be your fuse, usually your fuse will be of 30 ampere only maximum. Yeah, bigger fuses are there. Usually like if you say ampere, 1 ampere, 2 ampere, like that, it is pretty high. So in devices, electronic devices, it will be usually some microampere, milliampere and ampere, let's say, right. When it comes to resistance, ohms, very less ohms are used. Kilo ohms, mega ohms are the norm. And Henry, usually it will be let's say micro Henry and millihenry. Farad, it is microfarad. Millifarad capacitors are very rare and it is very difficult to make them. So usually it is microfarad only. But in our course, we won't be taking this practical thing into consideration. Usually we will be dealing with these things, volt, ampere, ohm, Henry and farad. Because our topic, our paper, this network theory is a very idealized paper. It is a very abstract sort of thing used as an analysis tool, right. It is sort of, not sort of, it is many a times it is detached from reality. It is a modeling tool or it is an analysis tool. Okay. So with that, let's wind up this lecture. I'll just go through what we started. First, we defined a node. What is a node? Then we went through the concepts of mesh and loop, right? What are the differences? Then the relationship between mesh, node, loop and branch, right? Then there was, we defined Ohm's law. From here onwards, I think this was sort of like a physics class, right? So Ohm's law, different forms of Ohm's law, the electromagnetic form and the circuital form, right? That is, we started with the this is the actual let's say original form, not original form because there are even other forms also, but for our purpose we derived this from this, right. And then we moved on to gave some basic definitions regarding what is voltage, current, resistance, and whatever we mentioned for resistance, it is applicable to inductance and capacitance. And then we discussed the actual relationship between the EMF or voltage, current and the impedance, right, resistance or impedance. Then I posed a question to you. I hope you get back to me. Then we gave a basic definition regarding what power is, and then we discussed the units of the terms, right. So with that, with this I am winding up the basic or introduction, notations, symbols, definition, those parts. So from the next lecture onwards, we will dive into network analysis or network theory. So in the next lecture, we will start with the Kirchhoff's laws, KVL, Kirchhoff's voltage law and Kirchhoff's current law. Thank you.